So next we will find the condition for the secondary maxima. We have seen that when alpha cos alpha minus sin alpha equal to 0, alpha cos alpha minus sin alpha equals to 0, d2y d alpha square was less than 0, that is, this gives us the position of the secondary maxima. So which gives us alpha equals to tan alpha. Okay. Now if we solve this equation for alpha, then we can find the position of the secondary maxima. Okay, but this equation alpha equals to tan alpha cannot be solved by analytical method. Okay, because this equation is called transcendental equation. Okay, transcendental equation means if one of the term is an infinite, if we expand in this equation, if there is a term which can be expanded in using infinite series, then that equation is called transcendental equation. So if you expand tan alpha, you will see that it will be an infinite series. Okay, some other examples of transcendental equations are the log series, logarithmic series, or exponential series, etc., because they can be expanded into infinite as a sum of infinite terms. Okay, so what we have to do, we have to take the graphical method. Okay, so for that we will draw one graph for alpha, another for tan alpha. So if we do that, the intersection, the points where these two curves intersect, those points will be the solution of this equation, that will give us the values of alpha. So next here we have drawn the two curves. This is the y equals to alpha, and these are the y equals to tan alpha. So y equals to tan alpha curves are a bunch of discontinuous curves. Okay, so one over here, this is another tan alpha curve, this one. Okay, and here we have the y equals to alpha straight line passing through the origin, which has a slope of 1, means this angle is 45 degree. The straight line is making an angle 45 degree with the x-axis. Okay, so here, so you see these two curves intersect this tan alpha curve at P, then the next curve at Q. Okay, then there will be other curves. If we draw for more curves, okay, then we will see that this y equals to alpha straight line will continue to intersect them at points. Okay, and then this curve is being intersected by y equals to tan alpha, y equals to alpha straight line at P prime, and then this curve at Q prime, etc. Okay, so you see now y equals to tan alpha curve. If you now try to remember the values of alpha, tan alpha, so at alpha equals to 0, tan alpha equals to 0, which is this one. Okay, then at pi by 4, tan alpha at 30 degree, tan 30 degree will be 1 by root 3. Then at alpha equals to 45 degree, tan alpha will be 1. Okay, then at tan alpha equals to 60 degree, tan 60 degree will be root 3. Okay, so in this way the value of tan alpha increases. So you see from 0 its value increases. Okay, and when it reaches pi by 2, tan alpha is infinity. So infinity means we have to go up to infinite distance along y-axis to find the value of tan pi by 2. Okay, so that's why here we have drawn a dotted line passing through the alpha equals to pi by 2. Okay, now if we extend this y equals to tan alpha curve, this curve will reach this dotted line at after going up to infinite distance along y-axis. Okay, so that's why here this line is almost parallel to this alpha equals to pi by 2 dotted line. Okay, similarly for the negative values of alpha, we have got the exact values, only their negative counterparts. Okay, so at alpha equals to minus pi by 2, tan alpha will be minus infinity. Okay, so this line over here around minus pi by 2, it is going parallelly up to infinity. Then in this way at alpha equals to pi, tan pi will be 0, so that's why it is 0. Okay, then again when the tan alpha will be infinity, when it is 3 pi by 2 and its negative counterpart at minus 3 pi by 2. Okay, so that's why again around 3 pi by 2 this line started going parallel to this alpha equals to 3 pi by 2 straight line, that is it has an infinite value at 3 pi by 2. Okay, so this line will meet this dotted line after going infinite distance. Similarly, again at alpha equals to 5 pi by 2 and its negative counterpart minus 5 pi by 2, tan alpha will be plus infinity and minus infinity respectively. Okay, so this we have a number of discontinuous branches of tan alpha. Okay, and you see this straight line intersect each tan alpha curve at some point. Okay, so what are the values of these points where these two curves intersect? So the points of intersections are from this diagram we have shown only this 4 points P, P prime, Q, Q prime, etc. Okay, so at P, what is the value of alpha? So if you look at this diagram at P, you see it is nearly equals to 3 pi by 2. Okay, but it is not exactly 3 pi by 2. Okay, so at point P, what is the value of alpha? At point P, alpha is nearly 3 pi by 2. Okay, so at point P, alpha has some value slightly less than 3 pi by 2. Okay, but it is not 3 pi by 2. Okay, it is slightly less than 3 pi by 2. So we can say that alpha is almost approximately equals to 3 pi by 2. And what about at P prime? So at P prime, you see its value is slightly greater than minus 3 pi by 2, but it is not exactly equal to minus 3 pi by 2. So we can say that at P prime, alpha is approximately equal to minus 3 pi by 2. Similarly, again at Q and Q prime, you see the value of alpha at Q is slightly less than 5 pi by 2, but it is, so we can say that at Q, alpha is approximately equals to 5 pi by 2, and at Q prime, the value of alpha is slightly greater than minus 5 pi by 2, so we can say that it is approximately equals to minus 5 pi by 2. So at these points of alpha, okay, so in this way if we draw further curves on both the sides, you will see that the next value of alpha, where there will be intersection between these two curves y equals to alpha and y equals to tan alpha, are 7 pi by 2 and minus 7 pi by 2. Okay, so at these values of alpha, there will be the intensity on the diffraction pattern will again be maximum, but their intensity will be less than the principal maximum, but of course greater than the minimum intensity, where the intensity is 0. Okay, so we can say that the directions of secondary maxima, where the directions where the secondary maxima occurs are alpha equals to plus minus 3 pi by 2. This is the approximately value, not the exact value. Then again at plus minus 5 pi by 2, again approximately, then again approximately at plus minus 7 pi by 2, etc. Okay, so now if we put the values in the general expression for intensity, we can find the intensity of the various secondary maxima. So if you remember, the intensity of the principal maximum was I0. Okay, and what was the general expression for intensity pattern? It was IP equals to I0 sin alpha by alpha whole square. So at the first secondary maxima, you see alpha equals to plus minus 3 pi by 2. Okay, so plus minus 3 pi by 2 means, plus means on one side of the principal maximum, minus 3 pi by 2 you will get the another secondary maximum on the other side. Okay, so for the first secondary maximum, alpha equals to plus minus 3 pi by 2. So the first secondary maximum, let us denote it by I1, which will be I0 sin plus minus 3 pi by 2 divided by plus minus 3 pi by 2 whole square, which gives us the value of 4I0 9 pi square. Okay, you can try this one, because sin 3 pi by 2 this is equals to 1. Okay, then in the denominator it will be 9 pi square by 4. 4 goes in into the numerator, so we will have 4i0 by 9 pi square. Okay, which is approximately equals to I0 by 22. Similarly, this secondary maximum alpha is plus minus 5 pi by 2. Okay, so what will be the intensity of the secondary maximum? It will be I0 sine plus minus 5 pi by 2 divided by plus minus 5 pi by 2. Okay, whole square. Again, this sine 5 pi by 2 will be plus minus 1. Okay, which will be square. Then if we take this square, it will be 25 pi square by 4. Okay, so it will be 4 I0 by 25, which is approximately I0 by 61. Okay, so in this way you can find the higher order secondary maximum. Okay, so now if we draw the intensity distribution curve for the diffraction patterns for the single slit, so what will be the nature of this curve? So the intensity distribution curve, you see, suppose along x-axis, so this is our y-axis. Along x-axis we plot alpha, and along x-axis we plot the along y-axis we plot the intensity. Okay, so at alpha equals to 0 we get the central maximum, principal maximum. Suppose it is the highest maximum. Suppose this is the I0. Okay, then we have pi minus pi. Okay, then 2 pi minus 2 pi, then 3 pi and minus 3 pi. Okay, then over here we have 3 pi by 2, and here minus 3 pi by 2. Then here at the middle bit of 2 pi and 3 pi, it is 5 pi by 2, and here it is minus 5 pi by 2. So at pi alpha equals to 0, the intensity is maximum, we get the principal maximum. Then on the either side the intensity decreases and we get the first minimum at pi and minus pi. Then again the intensity increases and we get the first secondary maximum around plus minus 3 pi by 2. Okay, so around 3 pi by 2 we will draw at 3 pi by 2 only we get the first maximum, first secondary maximum. Then again the intensity decreases, we get the second minima at 2 pi. Okay, similarly on this side also we get the first secondary maximum around minus 3 pi by 2. Then intensity decreases, we get the second order minima at minus 2 pi. Okay, just like at plus 2 pi. Then again intensity increases, we get the second secondary maximum around 5 pi by 2. Okay, so on the this side also we get the another secondary maximum at minus 5 pi by 2. Then intensity decreases, we get the third minimum at 3 pi. Okay, in this way we get the intensity distribution pattern. So this is the principal maximum. Okay, and these two are first order minimum. Okay, and over here we get the first secondary maximum. Okay, so first secondary maximum, this one is the same. Then we get the over here we get the second order. Okay, these two are the second order minima. These two are the second order minima. Then we get the secondary maxima I2. Then these two are the third secondary maxima, and these two are the third minima. So in this way we get the intensity distribution pattern for turnover diffraction for single slit.